So today we're going to integrate some more rational functions. Remember, all the integrating of rational functions we need is these three cases: degree 0 over degree 1, degree 1 over degree 2, and degree 0 over degree 2. Every other rational function, the integral is just going to be some combination of these three with some variations. But here's the, these are the three concerns that only having these three integrals raise. If q of x has an x term, then we need to fit it into these three cases. So we use completing the square to fit it into the quadratic with complex zeros to make it look like the 1 over 2 or the 0 over 2. If the degree of p of x is greater than or equal to that of the degree of q of x, that's the degree of the top is bigger than the degree of the bottom, then we have an algebraic answer for that. So notice that none of our three cases, the degree of the numerator is greater than or equal to the denominator. 0 over 1, 1 over 2, 0 over 2. So we use long division to rewrite our improper fraction as a mixed number, and then we'll have to integrate the remainder as an integral into a rational function. But then there'll be that whole number part, which will be just a polynomial. So we'll get a polynomial plus a rational function where the degree of the numerator is less than that of the denominator. And finally, if q has a real 0, and to further clarify, and the degree of q is greater than or equal to 2. So really the focus is, does q have a real 0? Because thinking ahead to our three cases, I only care about degree 1 in the denominator or degree 2 in the denominator. If q has a real 0, that rules out these two cases. That means we should be looking at some bunch of these. So if q has a real 0, that's all we really need to say. But let's include, since we're new, and the degree of q is greater than 2. So we're looking at quadratic or higher degree with a real 0. Unsurprisingly, I'm grouping these all together because they all have algebraic answers. So if the q has a real 0 and the degree of 2 is greater than or equal to 2, we're going to do partial fraction decomposition. All right. The idea behind partial fraction decomposition is undoing an addition problem. So yesterday we added 5 over x minus 3 plus 2 over x plus 1 and came up with 7x minus 1 over x squared minus 2x minus 3. Classical algebra problem. This is your algebra teacher saying, hey, do you remember fractions? And you're like, oh, yeah. And they're like, oh, do you also remember polynomials? And you're like, oh, yeah. Now we're just going to combine those two things. Take fractions, but instead of the numbers, they're polynomials, and do the same stuff. And then we find out that we didn't really know what we were doing with all those numbers in the first place, but that's okay. That's why we do algebra. So partial fraction decomposition is the reverse of that. We're taking our sum and breaking it up, taking our rational function and breaking it into a sum, subject to some rules. If I want to say break an integer into a product of other integers, I've got one choice, a product of primes. 6 is 2 times 3. That's it. 2 times 3 is always 6. 6 is always factored into 2 times 3. That's how multiplication works. There are rules. Addition is very laissez-faire about the whole thing. Break this 6 into 2 integers. So I go, all right, how about 1 plus 5? Or 2 plus 4? Or 3 plus 3? 0 plus 6? How about -1 and 7? Do you like that? So breaking things into a sum is either trivial or difficult. It depends on what rules we come up with for that sum. If that sum is whatever you want, then yeah, breaking things up into a sum is no trouble. But here we want something specific. Here's what we're going to be looking for. We want to rewrite our integral, our rational function into a sum where the denominators of the terms of the sum are the factors of the denominator of our rational function. Everybody got that? Did you write that down? I said it out loud, exactly what we're going to be doing. No. Don't write that down. That's just another example of English being really shitty for communicating math. What I want is to take my rational function and I want to make it terms. And the terms, the denominators of the terms are factors of the denominator of our rational function. The denominators of our terms are factors the denominator of the rational function. Oh, let's say starting rational function. Because I was trying to think of the right word and it's not coming to me, so I just pick something that's close. Just get a word that's within epsilon. We've exited the part of the room where I can just randomly throw some fractions together and have them work out. I got to plan a little bit more. All right. So if we were going to integrate this function, let's not do this in the context of integration. Let's remove the algebraic part, because I don't want us to think that by doing this, we're integrating anything. We're getting this function ready to integrate. So first thing we check, it's not substitution. 2x plus 3, I don't have a multiple of 2x plus 3. 5 times 2x is 10x, but 5 times 3 is 15, not 29. We don't have a substitution. Although, think about 10x plus the 15, that's what will make it a substitution. Think about what's left over and think about making two fractions, and then we'll come back to this. Just think about, from an integration standpoint, what the substitution might look like. So put a pin in that one. What we're going to notice is that the denominator x squared plus 3x minus 10 is quadratic and it has real zeros. We might recognize this because we might recognize this as factorable. We might say this is factorable and it factors, this has factors x minus 2 and x plus 5. So we notice that the denominator is quadratic with real zeros. That's what makes us want to do partial fraction decomposition. So I want to break this fraction, 10x plus 29 over the x squared plus 3x minus 10, into a sum of fractions. And the denominators of that term, those terms, are going to be factors of my original denominator. That's one of the words. I was trying to think of that word earlier. Original. Oh well. I want to write this 10x plus 29 over the x squared plus 3x minus 10 as a sum. Too many options. I want specifically the sum where the denominators of those terms are factors of my original. So I want something over an x minus 2 plus something over an x plus 5. Now we need to figure out what the numerators are. That's going to be our job. We have a big advantage here. We know that the numerators of these fractions must be constants. At the most, they're just constants. The degree of the numerators of the terms can't, in the sum, can't suddenly become greater than the degree in the denominator. If I put an x up here, that's going to produce an x squared when I multiply by the x plus 5. I don't have any x squareds. There's no x terms up here. If there's an x squared term up here, I multiply the x squared term times x plus 5, I get an x cubed. There's no x cubed is in the numerator. So I know that there's no x squared numerators in my sum. So we have an advantage. The numerators in our sum must be constants. The numerators in the sum must be constants. Now, this is only going to be true. We can't take this out of context. This is only going to be true if our original rational function, the degree of the numerator, is less than or equal to, or less than, sorry, strictly less than that of the denominator. So this numerators in the sum must be constants. That offer only applies in the case of the degree of Q, the degree of P being strictly less than the degree of Q. I just put it right here. I was going to put it up here for some reason. So some restrictions apply. The numerators of the sum must be constant so long as we are actually ready to do partial fraction decomposition to begin with. And that means the degree of the numerator must be less than the degree of the denominator. Fortunately for our heroes, if that's not the case, we have an algebraic answer for that. We do long division, break off the fraction, and do partial fraction decomposition on that term. So this is not a difficult restriction to meet. So the numerators in the sum must be constants. Now all we have to do is figure out what those constants are. Let's do the traditional route first rather than the shortcut. We're going to add these fractions and then equate coefficients. So after the number, once you write what your sum should look like with your unknown numerator and numerators, you just add those fractions together. So I have a times x plus 5. I need to multiply this first fraction by x plus 5 over x plus 5. So I have a times x plus 5 plus b times x minus 2 over our common denominator of x minus 2 times x plus 5. So I just take those two terms. I'm going to put them together to see what has to be true of a and b. I'm going to simplify this numerator. I've got ax plus 5a plus bx minus 2b. Now notice I said add the terms, then equate coefficients. So I'm going to gather my like terms. Ax plus bx is a plus b times x. And the constants are 5a minus 2b. You can see that I didn't have this one prepared beforehand. Whenever this happens, I always think to myself, I don't need to write it down. I can remember 4 numbers. But the fact is, no, I can't remember 4 numbers. I couldn't remember 735, -2, and 6. Or positive 3 and -6. I couldn't even just read those numbers. Not trying to cover up my work. I'm just need the real estate. So what we see is that we have a plus b is the coefficient of the x. And then 5a minus 2b is the constant. Now what we have on what we need to do now is remember that this fraction that we just put together is still equal to what we started with, 10x plus 29. That fraction is still equal to the rational function we started with. If these two fractions are going to be equal, then the coefficients of x must be the same and the constant term must be the same. So we end up with the system of equations. A plus b is equal to 10. That's from the x coefficients, and 5a minus 2b is equal to 29. If these two fractions are going to be equal, then the coefficients of the numerators must be the same. So the a plus b on the right side must be the 10 on the left. 5a minus 2b must equal 29. So we have this resulting system of equations. We can solve this however we like. I think I'll multiply the first equation by 2 and add it to the second equation. I'll do some row operations, but I'm not going to write the entire matrix. I'm just going to do the row operation. So if I multiply this by 2, I get 2a plus 2b is equal to 20. I'm going to take row 1 and multiply by 2. Then I'm going to add these two equations together and get 7a is equal to 49. So from here to here, I did row 2 minus or plus my new row 1. And then I'll just divide by 7 and find out that a is equal to 7. If a is equal to 7, then 7 plus b is equal to 10. So b is equal to 3. So now we know that 10x minus 29 over x squared 3x plus 3x minus 10 is equal to 7 over x minus 2 plus 3 over x plus 5. In the context of a calculus problem, I would have asked you to integrate (10x minus 29). Spelled 29 wrong. Dang it. I can't erase that precisely. So in the context of a calculus problem, I would be asking you to integrate this rational function. You would recognize that the degree of the numerator is less than that of the denominator, and that the denominator is quadratic with a real 0. So then you do partial fraction decomposition. All the stuff that we did decomposing this fraction is for this step right here. So we can write this in as the integral of 7 over x minus 2 plus 3 over x plus 5. So that we can easily integrate our terms. So the idea is we're going to rewrite our starting rational function as a sum. But we want a specific sum, a sum where the terms are going to be easy to integrate. All this comes down to knowing what the terms of the sum can look like. So it all comes down to knowing what the terms of the sum can look like. And knowing the rules for partial fraction decomposition, knowing that you might need to lead with long division if the degree at the top is too much. So what I'm going to secretly do now is come up with a problem. I'm just full transparency. I'm just right in front of you. Because I can't remember what the problem was. If I had any kind of memory whatsoever, I would just write down. Question? Uh-huh. Yes. Thank you. So I'm going to start by just writing down. I can't remember what the problem was. It's on a Post-it note up in my office, but the Post-it note is up in my office and not here. Not exactly useful. So I'm just going to have to rebuild it. But here's what I want. I want to have a real zero, but I also want to have a quadratic factor. So I just need to decide on a real zero and a quadratic factor. And then I just need to make two fractions. So what I want, so this is secretly happening. What I'm thinking is that I want, let's say we want to integrate 7 over x minus 3. I'm going to keep it to plus. I just need another number, but my denominator is going to be quadratic. Oh, wait. Then I remembered why I didn't bring that Post-it. See, it all comes back eventually. So I secretly plan what I want in advance. Now you can see that this is what I want to be looking at because this is going to be easy to integrate. This is going to fall into our 3 categories. I've got degree 0 over degree 1. Over here, I've got degree 1 over degree 2, and I'll separate out the -1 over x squared x squared plus 1, and that's going to be my degree 0 over degree 2. But I need to frighten people with a quadratic over a cubic. So, ooh, right? So we got to add these together. So it's 7 times x squared plus 1, and then a 2x minus 1 times x minus 3. Going to want to know what the denominator is. So it's going to be an x squared minus 3, x cubed minus 3x squared plus x minus 3. So my numerator is going to be 7x squared plus 7 plus 2x squared minus 6x minus x plus 3. So the one that I'm going to actually ask for is going to be 7 and 2, 11x squared. Let's see, minus 7x plus 10. Then I'm going to say, why did I add these on paper when I have a very expensive calculating machine in my pockets? Then I'm going to remember it's because I can barely read the expensive calculating machine sitting in my pockets. Incidentally, you can see what you're eventually going to, if you, one of the things that Wolfram Alpha will tell you is what you're eventually going to be looking at. Let's see. What are my alternate forms? Here it is. It should be 9x squared plus 5x plus 4. 7 and 2 is not 11. Let's see. Apparently I made a mistake here. Minus 6x minus x. Minus 1. Everybody see what I did here? This is the other reason I have to do this in front of you, to show you that I'm really bad at algebra. 2x, then minus 6x, yeah? Minus x, minus 3, 7x, 7, 2x squared, 7, 2x is 9x squared. That one's resolved. But I've got a minus 6x. This is a minus x, so that should be minus 7. Aha. Back to the aforementioned, I can't see the stuff on this machine. There we go. 9x squared, minus 7x plus 10. Whew. So this is the rational function I would ask you to integrate. So we don't just want to make them up on this end, because then it'll come out really messed up on this end. If you want nice integers here, start at your answer and work backwards. That was my strategy for chemistry. What do you want the maximum error to be? 5%? All right, so 5% means that this was this calculation. Then you'll have to weigh one thing. You don't have to burn up all your ingredients. I'm just kidding. I didn't cheat my way through chemistry. Much. I'm just kidding. I got multiple A's in that class. I got an A. The person sitting next to me got an A. The person sitting next to me on the other side got an A. The person sitting behind me got an A. I was wondering what all these fools were doing here, but there it is. So but then my high school chemistry teacher, it does make sense. What am I called? Well, Mr. Olson, why don't we just go backwards? And why don't I just believe you that this is what's supposed to happen? It's like, well, because you need to learn the lab stuff. I'm like, oh, but I've done the calculations. I can tell what's going to happen. He's like, oh, you're going to make a really shitty version of Mythbusters someday. Because most of Mythbusters is just a bunch of math. You can run the math and say, yeah, that's not how that works because of math. But that's not going to make a good show, because how many shows out there? Math busters. We go around and use math to bust stuff. I'll tell you what that's called. It's called Number File, and it's one of the best channels on YouTube. What are we talking about? Oh, yes. So I would do something like ask you to integrate x cubed minus 3x squared plus x minus 3. So here's how what happened. We're looking at this function. And you say, a rational function. You have to say it that way too. Got to be more dramatic. It makes the tests really loud, but also much funnier. Because you can find out when people get to problem 3. You're like, aha, a rational function. So immediately you start thinking about what you need for rational functions. The x term thing, that's not on the table. That's for when we're looking at the quadratic denominators with complex zeros. That's when the complete square thing comes in. So we move on to number 2. The degree of the numerator the degree of the numerator is less than the degree of the denominator, so we don't need long division. The degree of the numerator is less than the degree of the denominator, therefore, no long division. And then you start thinking, you start meta thinking about the problem. And then, well, Leach has been on and on about this stupid partial fraction decomposition. This must be a partial fraction decomposition problem. But let's think about why it's partial fraction decomposition, not because I said so, because I'm not going to be always there to tell you what to do. We notice that the denominator has a real zero. That's what tells us to do partial fraction decomposition. So the denominator since the denominator has a real zero, that means we're going to do partial fraction decomposition. This raises the question, how do we know that the denominator has a real zero? What's telling me that the denominator has a real zero, aside from the fact that I know exactly what the denominator is made of? What tells you that this denominator has a real zero? Since Q is odd degree, Q has to have a real zero. An odd degree polynomial, the ends go in opposite directions. In this case, we have an odd degree and a positive leading coefficient. So this function goes to infinity as x goes to infinity. And then the other side, negative infinity, does the opposite. The function goes to negative infinity as x goes to negative infinity. The ends go in opposite directions. That's the way we would have phrased it if you had been in my class for pre-calculus, but I haven't done that for a very long time. It only exists in my mind. But the ends go in opposite directions. So that's why we know that this polynomial must cross the x-axis somewhere. And at this point, you start thinking, man, I sure hope it's an integer. And fortunately for us, it is. So x cubed minus 3x squared plus x minus 3. What we want to notice, if we really have, we want to use our super algebra skills and recognize, aha, this is factorable by grouping. If I take an x squared out of the first two terms, I'm left with x minus 3. If I take a 1 out of the second two terms, I'm left with an x minus 3. So we notice that the denominator is factorable by grouping. So we got a lucky break. The denominator is factorable by grouping. We're not going to have to work hard for what that real zero is. Once you start doing factoring by grouping in your calculus class, you need to start thinking, oh man, how contrived is this? That's awfully convenient. Just like a video game. Will you take the item? Then it actually gives you a choice, as if you have a choice. Will you pick up the item? Well, yeah, because it's a puzzle item that I need for the next room. So you pick up the item, go to the next room. It's like, oh, what will you put in the key slot? I might call it the key that I just found in the room right before this. And then the video game designers all high-five each other. Hell yeah. Awesome puzzle, dude. Oops. So our denominator is factorable. The factors are x minus 3 and x squared plus 1. Those are going to be the denominators of our terms in our sum. So we want, this is still in the context of integration for reasons. I'm going to split this rational function into two terms. One term is going to have denominator x minus 3. The other term will have denominator x squared plus 1. That was the same as the first step that we did way back here. Denominators of our terms are factors of the denominator of the rational function. Denominators of the terms are factors of the denominator of the rational function. Now we have to put in our guesses as to the numerators. Over x minus 3, we get a. Notice that if over x squared plus 1, if I just put a constant, then a would be equal to 9 because that's the coefficient of x squared, and a times the x squared plus 1 is the only place that I'm going to get an x squared. But that would mean, well, other things. So we can't just put a constant over the x squared plus 1. We have to put the biggest thing that we might fit there. What we're trying to do is we're just putting our guess, and our selection of a and b constants for the numerators was we were fitting the biggest possible thing that could show up in that numerator. We have to put the biggest possible thing that could show up in each of these numerators. So over a constant, the degree has to be less. That leaves us with degree 0. So sorry, over the degree 1, we have to be 1 less. Over degree 2, the maximum is 1 less. So I have to put a generic linear numerator. Linear numerators go over quadratic denominators. Constant numerators over linear denominators. We make the numerators 1 less than the denominators. We know that we could stop here because we started with a degree of the numerator less than the degree of the denominator. That means we can continue that into our term. Here's what you need to do now. We have broken apart our rational function into terms with generic numerators. All we have to do now is figure out what the A, the B, and the C are. So that's your DVD bonus material question for today. Tomorrow we're going to lead with finding A, B, and C. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.